Good morning, class.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Morning, sir.
Good morning, sir.
Somebody is trying to mimic my voice to greet you. Well, yes, certainly. So let's go back to where we stopped in the last class. We talked about charging, and I said it involved, I spoke about 3 methods of charging, which is by conduction, by friction or rubbing, and by induction. In the 3 different methods, one thing which is common to them all is that after charging, the number of positive charges is no longer equal to the number of negative charges. The number of positive charges is no longer equal to the number of negative charges. So, charging by conduction, it involves the contact of a charged object with a neutral object, and it's useful in charging conductors. So when we say that the number of positive charges is no longer equal to the number of negative charges, in this, okay, let me take a pointer. Okay. So, okay, in this case, this is like a neutral conductor. And now we want to charge it with a charged body. This particular body is charged because it contains excess negative charges. When the charged body is brought close to to touch the neutral object, electrons, negative charges, will flow to the neutral objects because there are there are so many excess charges here. So part of the excess negative charges will flow to the neutral body, making it negatively charged. Another scenario is to think about hold on 1 minute, please. The other scenario is to think about a particular body that is also neutral. And now we have another body that is having excess positive charges. Sorry. So in this scenario, sorry, I need a pointer. So in this scenario, in the first scenario, we had excess negative charges and a neutral body. In the second scenario, we have excess positive charges and a neutral body. In the second scenario, when this charged body is brought in contact with the second charged body, we would have something of this nature. When there is a contact, positive charges will not flow to the neutral body. Positive charges will not flow from here to the neutral body. What will happen is that part of the negative charges will leave this particular body and will leave this particular neutral body and come to the originally charged body. So when a positively charged body, a body which is deficient in negative charges, which is deficient of electrons, is brought in contact with a neutral body, negative charges, electrons, electrons are the lighter, they are the mobile ones, they are the ones that have to move. So the negative charges will flow from this neutral body into the positively charged body. And when that happens, this body would be having fewer electrons than it had originally. So when this body has lost some of its electrons to the positively charged body, it will be having fewer electrons. And when it has fewer electrons, then we can say it is having a positive net charge. We can say it is positively charged. So in both scenarios, whenever we are talking about charging, whenever we are talking about about a body charging another body, if a body is becoming negatively charged, electrons flow into that body. And when a body is to become positively charged, electron leaves that body. So we don't talk about protons moving. And a good excuse can be attributed to the masses of protons and electrons, because protons are heavier than the electrons, and the difference in their masses are far apart. Okay. All right, it seems to have joints. Those. Oh, yeah, good. Excellent. So let's move ahead. So rubbing by friction, the difference is that in rubbing by friction, that would be similar to what we discussed on this slide, where we're using wool to rub plastic rods, where we're using silk to rub glass rods. And what happened there? There were transfer of electrons. If you recall, I did not mention protons were transferred. I will always mention electrons are transferred, because electrons are the major participants when we talk about electricity. So charging by induction involves bringing a charged body closer to another, close to a neutral body. So there is no need for physical contact, and charging can occur. Let me try to show something of that nature. Let's say I have a charge, a conductor. Standing on an insulator, and the conductor is having both positive and negative charges. If I come with a charged body, that is, let's start by saying, let's say the body is negatively charged, that is negatively charged, having excess of electrons compared to protons. When I bring the charged body, the negatively charged body, close to the sphere, when I bring the negatively charged body close to the sphere, what I would expect is that since it is negatively charged, we will have positive charges, excess of positive charges at this side of the sphere, while most of the negative charges would run to this side of the sphere. Why? Because negative charges on this neutral sphere, is it still neutral? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Because negative charges in this neutral sphere will be repelled by the negatively charged body that is approaching, and they will move to the other end of the sphere, leaving the right-hand side of the sphere to be positive. So when this charged body is taken away from the vicinity of this sphere, everything returns to normal. The atoms the charges are arranged randomly. But when the charge body is brought close, we have something of this nature. So if you come to this other end, if this particular charge body is brought and made to remain at this point, and we have this configuration, if you come to this other end and you ground it, that is, you touch it, this particular part can be said to be having excess negative charges. So when you touch this particular point, part of the electrons flow to the ground. When we touch this place, when we ground it, part of the electrons will flow to the ground. So if I can touch it and now remove my hand. So by touching it, grounding it, and removing my hand, part of the negative charges would have flown to the ground. When I take, sorry. When I take this particular body, this particular charge body, when I take it away, what will be left here? You know, I said some of this would have flown to the ground. Since they'll flow to the ground, let's assume that we have a few ones flowing to the ground. When that is done, when I take this particular charge body away, this formerly neutral sphere will now be having deficiency of negative charges. It will now be having excess of positive charges. Thereby, it can be said to be positively charged. Let's look at it in another way. Let's think about it in such a way that originally we had, oh my. Let's think about originally we have pen come out. Let's think about it that originally we have excess, we had a neutral. Let's return it back to normal. Let's return this charge body back to normal by saying we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8. 1, 2, 3, 4, 5. Oh my mind. We have 8 positive charges and 8 negative charges. When the charge body here, you know, the first scenario I've just talked about, I spoke about the charge body having excess negative charges and few positive charges, making it negatively charged. Now, let's think about it in such a way that we have excess positive charges. So let's think about this body having excess positive charges. When a body that is having excess positive charges of this nature, when it's brought close to a neutral sphere, what we should expect will be that the 8 protons or the 8 positive and 8 negative charges will be arranged in this manner. We'll be having the negative at this part, so we'll be having excess negative charges closer to the location of the positively charged body, and deficiency of negative charges at the other end. And that can be explained by saying that unlike charges should attract. So the unlike charges to this positively charged body are the electrons, and they will come closer to the charged body, leaving the other end to be deficient of negative charges. So when this happens again, you have brought the charged body close to this neutral sphere. The charged particles are no longer random. They are now responding to the presence of the field created by this charged body. There is no contact. It has just been brought close to it. And now you come to this particular corner and you touch it. When you touch it, the positive charges here would not flow to the ground. When you touch it, this is how we can be said that you have grounded it. When you touch it or when you ground it, this is the symbol for ground in electricity. What happens when you touch it or when you ground it is that electrons would flow from the ground and come in here with an attempt to neutralize the excess positive charges at this end. So electrons will flow from the ground and flow into the sphere with an attempt to neutralize the excess positive charges at this end. So in that place, electrons are flown in, and now you remove your hand, or now you disconnect the neutral, the originally neutral sphere. You will disconnect it from the ground. You know, since we said, oh, sorry, let me return the ground. I said electrons will flow from the ground with an attempt to neutralize. So we should have new electrons which are flown from the ground into the neutral sphere. They come in with an attempt to neutralize the excess positive charges at this corner. So when that is done and the ground is disconnected, what do we have left? We have a sphere which was originally neutral, but right now is having excess negative charges. Since it is having excess negative charges, then it can be said to be negatively charged. So when you take this positively charged body away from the sphere, it will not change the fact that this sphere contains more negative charges than positive charges. So by saying that, we can say that the sphere has been charged by induction. Okay, so like you can see from that electrons are the ones that flow to the ground, and the electrons are still the ones that flows from the ground. So the ground, when we say ground, the ground is a large body, which can be the earth itself, and it's a large reservoir of charges. So when you need electrons, it is always there to supply you electrons. And when you have excess electrons, it is always there to take the excesses that you have. So the ground is always there to take away the excesses. It's always there to supply electrons. So it can be referred to as a reservoir. So when you add electrons to the ground, it doesn't move. And when you take electrons from the ground, there is no significant change in the configuration of the ground. So this page talks about grounding, and it's a process of removing the excess charge on an object by the means of transfer of electrons between it and another object of substantial size. So the earth itself has substantial size. And if you by yourself, at least I expect it to be bigger than the charge sphere. So when you touch it, you have the capacity to absorb a few electrons or give out a few electrons that you won't even notice, but the small objects would notice and they would experience high difference in their net charge. When you open the pot of soup and there are so many meats in there, if you take one, nobody will notice. But if you open the pot of soup and there are just 4, if you take one, you take it at your own risk. So the act is so large, just like a large pot of soup. If you add a piece of meat, it will not know. And when you take 1 or 2, it won't even know. So let me look at what we have in the charts. Let us go from the ground. Doesn't mean that the ground is negatively charged. Okay, I think I've answered that question. The earth is a reservoir. It takes in the electron and it gives out the electron. There is no need to write your name and matric number in the chat. Then what else? What else? What else? Okay, I think some people raised their hands. Okay, they are now lowered. Okay. Okay. Okay, let me listen to Fumi.
Good morning, sir.
Good morning.
Yeah, thank you so much. I really learn a lot.
Please go straight to the question, please.
Okay, the question is this, sir. I just want to ask that why is it that the positive charge, I mean, the electron is the one that is flowing either from the earth to the body, or from the body back to the earth? Why is it electron and not the positive charge? Why
because
is it the negative charge?
Are lighter. The lighter charges are the mobile charges.
Okay, thank you, sir.
And let me take the last question before we proceed. Morakinyo.
Good morning, sir. My question is, what charge does the human body carry? And also this.
You cannot say the human body carries a charge. The human body is a body.
So why is it that we're not transferring electrons?
You cannot really say it has a charge, but you can say that it can take charges. It can take in electrons and it can also give out electrons, just like the ground. So it takes in electron, it takes out electron. It's really not realistic to say it has charges. So some parts of the body, when you move towards some charged material, some charged objects, the hair on your body may stand up to respond to the presence of electric field. So our body contains charges, and if you move close to an electric field and the charges on your body, some negative charges move towards the hair on your body, they may stand up. So that does not mean that you are charged. So a body is said to be charged when it is having excess positive charges than excess positive charges to negative charges, or the other way around, excess negative charges to positive charges. So it depends on the scenario. If you have lost electrons, then you can claim to be positive charges, but I will say the human body originally should be neutral because it's composed of chemicals, liquids, and many tissues that are expected to be compounds.
Okay, sir. Thank you very much, sir.
So let's continue. So having spoken about charges, charging, then it's important and also we need to remind ourselves that like charges repel, while unlike charges attract with forces described by Coulomb's law. So what is Coulomb's law? Coulomb's law helps in quantifying the amount of force. From this statement that says like charges repel or like charges attract, they tell us the direction of the force that is being applied. When we talk about force, force is a vector quantity and it is meant to be specified in terms of magnitude and direction. So this rule here, which says like charges repel and like charges attract, tells us the direction. When something is attractive, it moves towards you. And when something is repulsive, you move away from it, or you move to, or it moves away from you. When it's attractive, it moves the contribution that we gain from the knowledge of Coulomb's law. Coulomb's law states that the electrical force exerted by one charged body on another is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance separating them. So when we have two charged bodies, I say there is no need to write your names and magic numbers in the chat box. Let the chat box be reserved for questions and not for writing things that will drown important matters. So Coulomb's law, when we have two charges, if they are both positive, we will expect them to repel. We would expect this particular body to push this one away. Let me label them. Let's say this is A and this is B. We would expect A to push B away in this direction. We would also expect B to push A away in this direction, but with what amount of force? That amount of force depends on the product of the charge of A and the product of charge of B. So when the charges on A or B increases, then the force with which they will push themselves away will increase. It also depends on the distance separating A and B. When A and B moves closer to each other, the force with which they will push themselves away will increase. But when A and B are far away from each other, the force with which they will push themselves away will reduce. So Coulomb's law can be said in two sentences to say that the force of attraction is directly proportional to the product of their charges. Charge is represented here as Q, Q1 and Q2. In this case, we are talking about two charges, two charged bodies. So the force is directly proportional to the product of their charges. So Q1 is the charge of body 1, Q2 is the charge of body 2. And the force is also inversely proportional to the square of the distance separating the two charges. So R is used to define distance here. You can see specified it as distance R. So the distance of separation between the two charges, the larger it is, the smaller the force that will be experienced by the charged bodies. And there is also a constant of proportionality, which is called K. So I will say F is directly proportional to, okay, it's over here anyway. But I will say F is directly, come back here. Well, I will say F is directly proportional to Q1, Q2, and inversely proportional to R squared. Then we have introduced a constant of proportionality here, and the constant of proportionality is defined as 1 over 4 pi epsilon naught, where epsilon naught is defined as the permittivity of free space. And the value is given as 8.85 times 10 raised to the power minus 12 per Newton per meter square Coulomb square. So when we say 1/4 pi epsilon naught, approximately, we can say it is also equal to 9 times 10⁻⁹ Newton meter square per Coulomb square. So Coulomb's law obeys the superposition principle. That is, Coulomb's law, we spoke about Coulomb's law we refer to two bodies. When we defined Coulomb's law earlier, we refer to two bodies. So, but what if we have more than two bodies? So when we have a certain body A, another body B, and a certain body C, and we want to know the effects of the charge on body A and the charge on body B on body C, we can deal with A and C, forgetting that B exists. Then we later deal with B and C, forgetting that A exists. By so doing, we can easily add together by saying the force of, when we want to know the impact of the forces of A and B on C, we can start by determining the impact of the force of A on C, then determine the impact of the force on B on C. Then we add them together. That's one of the beauty of vectors. In vectors, you can easily add things together and you'll be on the right track. So what this is saying that the total force acting on C can be said to be the force of A acting on C and the force of B acting on C. So we'll see examples, and that will not be a problem very shortly, if time permits. It is another property is that Coulomb's force, it's a conservative force. A conservative force is a force with the property that the work done in moving a particle between 2 points is independent of the path taken. So when force A moves force C through a certain distance, maybe through repulsion, regardless of the path taken, the work done can be computed by just considering a straight line. So even if it pushes it through a zigzag motion, through a straight line, the work done is conserved, is independent of the path taken. And it's a central force. It acts along the line joining two charges. So it's a central force. A will push C away on a straight line, while B will push C away on a straight line if A, B, and C are like charges. A will push B away on a straight line if A and B are like charges, while B would attract A on a straight line towards itself if B is having an opposite charge. So we have two different charges. So when it's not positive, it will be negative. Nothing sits on the fence except the neutron. And we don't have any business to do with the neutron. We are interested in positive charges, negative charges. So this is an example. The electron and proton of hydrogen atom is separated by, on the average, by a distance of approximately 5.3 times 10⁻⁻11 meter. Find the magnitude of the electric force between the particles. So the question is saying the magnitude. The question is not interested in the direction, but if you're interested in the direction, you will expect them to attract each other. But since it's just the magnitude, so we are going to think about it in a crude way, to think about this point to be the proton, and this point to be the electron, and the charge of a proton is 1.6 times 10⁻⁻19 Coulomb, while the charge of the electron is 1.6 times 10⁻⁻19 Coulomb, the magnitude of the charge. And the distance of separation now, the distance between the two charges is said to be 5.3 times 10⁻⁻11. So it is to say that Q1 Q1 is equal to this. Q2 is equal to another 1.6, and you can say R is equal to 5.3 times 10 power minus 11 meter. And I start by checking if in the SI unit, then I go ahead to say that force is equal to Q1 times Q2 divided by R squared, not forgetting the constants of proportionality K. And that can be approximately 9 times 10 to the power 9, which is the constant of proportionality, times Q1, which is 1.6 times 10 to the power 19, minus 19 rather, times Q2, which is 1.6 times 10 to the power minus 19. But this is, excuse me, 9 times 10 to the power 9, that's, okay, sorry. So, and the, divided by the R squared, which is 5, come on, come back here. 5.3 times 10 to the power minus 11. The denominator unit is in meter. When we square it, it becomes meter squared. And the numerator, this, where is my pointer? This is in Coulomb, this is another Coulomb. Well, this is measured in Newton per Coulomb square, meter square. So when you do the, what do you call it, dimensional analysis, the units anyway, without wasting our time, is to say that the unit of force is Newton. So whatsoever you get here, Newton, will be the force, magnitude of the force, electric force between the electron and proton of the hydrogen atom. So like I said before, force is a vector quantity, and it is important when applying Coulomb's law. So let's look at this carefully. Let's look at this carefully. Here, in this case, we have a charge Q1, and we have another charge Q2. Q1 is positively charged, while Q2 is positively charged. So there is a language with which we need to learn so that when we are talking henceforth, we would not be wasting time saying too much of stories before we get ourselves. One of the languages say that when we talk about the distance, okay, let me start by this. Okay, the distance of separation between Q1 and Q2 is R. So when we have Q1 and we have Q2, we would expect them naturally to repel. So what that means is that the force that Q1 will exert on Q2 can be regarded as F12. The force that Q1 will exert on Q2 is defined as F12. So F12, when we say F12, I'm talking about the force that Q1 will exert on Q2. So now we assume that Q1 is the chairman here, is the landlord of this territory, and it is now pushing the rival positive charge away from its premises. When it's pushing the rival away from its vicinity, it will push it in a straight line in this direction, and the force can be defined as a vector quantity defined as F12. And the direction with which it will move is in the direction of this unit vector R12. So that is, let me call it scenario 1A. So the scenario 1B will be that we take this Q2 to be the landlord of this premises. And it is, since it is seeing another rival here, it is pushing the rival away. The force with that Q2 will exert on Q1 is defined as F21. Q2 exerts a force of F21 on Q1, while Q1 exerts a force of F12 on Q2. So you need to sit down and digest that so that you don't move too slowly. So when in scenario 1B, where Q2 is the landlord, is the chairman, it's repelling Q1 in the direction R21 with a force F21. So you can see that the forces direction of their using to Q2 is same as the force with which Q2 is using to repel Q1. So let's move on to scenario 2. Oh, sorry, it's labeled A and B. So let's take 2. And now in this case, we have Q1 to be positive and Q2 to be negative. Naturally, the first thing that should come to your mind is that Q1 and Q2 are opposite charges and they should attract. So the first question is that what is the force that Q1 is exerting on Q2? Q1 is exerting a force of F12 on Q2. Well, and what that means is that because it is a negative charge, it will attract it. So you can see that F12 is pointing towards Q1 because Q2 is having a negative charge. That is the reason why Q1 is attracting Q2, because Q2 is having an opposite charge. It's having the different charge. So it is meant to attract and it is meant to point in the direction of Q1. On the other end, the last final scenario is that what is the force that Q2 is exerting on Q1? Q2, now we imagine Q2 here to be the chairman, to be the Babalaye of this territory. Q2 has noticed an opposite charge here and is going to attract it. That's nature. Q2 will attract this in a straight line in this direction with a force called F21. Q2 attracts Q1 with a force F21. It's attractive because they are opposite charges and it will attract in a straight line, and the force is regarded as F21. So the F21, F12, they are conventions so that when we say F12, F21, you will not be lost. Okay, so when Q1 attracts, Q2 attracts Q1, Q1 attracts Q2. Q2 attracts Q1 with force F21. Q1 attracts Q2 with a force F12. The magnitude of F12 and F21 are equal, but the direction of impacts are opposite to each other. So, and that should remind us of Newton's third law of motion. So when the force is acting on another, when the force is acting on the body, we should expect motion. That's Newton's second law. And that force should also obey, the forces should obey the third law. That is, the forces should be equal and opposite. Okay. Let's look at this example. How many moments do we have? Let me see if we still have Let me see what you have after here. Okay. Come back. Okay, I'll just describe what should happen here, then I'll leave it to you to go get it done. So the question is that consider, excuse me, consider 3-point charges located at the corner of a triangle. So these are the 3-point charges. We have Q1 down here, we have Q2, and we have Q3. And they are located at the corners of a right triangle, that is a right-angled triangle, as shown. So this is, that's what you are seeing at the base of the screen. Q1 and Q3, that is Q1 and Q3, they have charge of 5 microcoulomb. 5 microcoulomb. When we say microcoulomb, what is meant is times 10 raised to power minus 6 coulomb. And Q1 is also 5 times 10 raised to power minus 6 coulomb. And Q2 is minus 2 microcoulomb. So what we have here, Q2 is 2, the magnitude is 2 microcoulomb. That is 2 times 10 raised to power minus 6 coulomb. And A is 0.1 meter. So this point is 0.1 meter. The distance between Q1 and Q2 and Q3 is 0.1 meter. The distance between Q2 and Q1 is 0.1 meter. And the distance between Q1 and Q3 is 0.1 root 2 should be 1.14 times 0.1, that should be 0.1414 meter. So what should be done is that, so the question says, find the resultant force acting on Q3. The question is saying the force acting on Q3, that is F3. Force is a vector, and that force will be equal to the force of Q1 acting on Q3 plus the force of Q2 acting on Q3. So the force of Q1 acting on Q3 plus the force of Q2 acting on Q3 will be the total force F3, that is the force that is exerted, the force that is acting on Q3. Then the question should now be, what is F13 and what is F23? F13 should be equal to K Q1 Q3 divided by R13. And we should also talk about the unit vector R13 caret. And what is K? We know our K. What is Q1? We know Q1 to be 5 microcoulomb and Q3 to be 5 microcoulomb. So that's times 5 micro times 5 micro divided by the distance of separation between them is 0.1414. 0.1414 squared. So when you multiply all this together, you should have the magnitude. Then what will be left is the direction R13 caret. So what is R13 caret? R13 caret should be the, it's a unit vector. The magnitude is 1. Oh, our time is up. Unit vector, the magnitude is 1. I think it's better we talk about this on Thursdays because the time is up. So R13 is the magnitude, and sorry, R13 is the unit vector. So let me just try to describe it, and I will stop thereafter. So we've said F13 is a force that Q1 is exerting on Q3. F13 is a force that Q1 is exerting on Q3. And that force is repulsive. It should push 3 away in this direction. It should push 3 away in this direction because it's repulsive. Q1 is positive, Q3 is positive. So it should push Q3 away in this direction. So when it pushes 3 away, then we'll be interested in how is this direction, how is it defined? That is what R13 caret says. That is what R13 carets, what we have here. That is what it tells us. It tells us how is this direction, how is it defined? And if we want to define that, we define it in terms of x-axis and y-axis. X-axis and y-axis. We'll begin from this point on Thursday. Sorry, I won't be able to take questions because of the time. Something involves induction involves grounding of objects. Charging by induction involves grounding. Yes, I've said that. Q3 pushes Q3 in what direction? Yes, so we continue from this place on Thursday.